Hello everyone, and welcome to Lecture 14 on Ethernet. Last time we kind of introduced this topic of the link layer by talking about medium access control in general, and today we're going to be talking about how it works in practice with a few additional real protocols. So, introducing medium access control last time, we defined the link layer and medium access control as a way to handle sharing of a physical link or a medium with multiple nodes that want to communicate on that same link or channel. And another word for that is multiple access protocol. It's a way to decide how to share the link. And the key goal here is to avoid collision. If two nodes try to send at the same time on that shared link, the messages will collide, they'll overwrite each other, and that data will be lost, which is inefficient. It has to be retransmitted. And there are three basic classes of these medium access control protocols for sharing a link. Channel partitioning was the simplest one. Examples of that include frequency division multiplexing and time division multiplexing, where you break a channel into several virtual channels that have like a fraction of the total capacity. Turn taking is a variation of that, where you have a dynamic scheduling of who uses the different time divisions. That can happen with polling, where there's a central leader that decides who gets to talk when, or with token passing. And another approach that doesn't require centralized control is random access. Aloha was a historical example to introduce the idea, and then we saw later on that Ethernet uses CSMA-CD, carrier sense multiple access collision detection, which involves listening to the channel, and if it's free, send your data, but then while you're sending, you listen for collisions, and if there's a collision, you stop. Okay, we said that was used by Ethernet and Wi-Fi. Okay, so we're going to talk more about Ethernet today, not really about this specifically, because we'll see that there are some additional, I guess, design elements of Ethernet that have evolved over time, besides just the CSMA-CD way of handling a shared link. Okay, so I thought it'd be fun to introduce this topic by showing a photo I took a couple years ago of one of our IT staffers at Northwestern in a IT closet in the tech building, where there's just a ton of Ethernet cables running into patch panels, and there are switches in here somewhere. I think you can see them on the left-hand side. Those are the switches. We're going to talk about Ethernet switches today, which are devices for connecting multiple Ethernet cables into a subnet. Okay, and it's funny to see these like huge bundles of cables running throughout the ceilings of the hallways, right? So we'll learn a little bit more about how that works today. Before we do that, before we talk about Ethernet, we're going to talk about DOCSIS cable. This is really pretty interesting because it combines many different medium access control protocols into one system. And DOCSIS is the standard for cable internet delivery to homes. So on the top right, you see one of these coaxial cable wires that you probably have seen. You probably have not seen it stripped away like this, but it's a solid core, metal core in the middle, which is the conductor where the data is sent, and then you have an insulating sheath around the edge that keeps noise out. Because of this insulation, it is really low noise and can send really high bandwidth signals, right? So this is an ideal kind of wire for communications, and it has been used for many decades for cable television. And then when people wanted to have internet access in their homes in large numbers, cable companies started selling internet access over the very same cables that they had laid out in neighborhoods. But because the original design of this network was for delivering cable television, that's a broadcast, right? It involves sending the same channels to every customer, although I guess some customers can pay more for different channels. That's handled by a cable box in your home that kind of filters out certain channels. But generally, there's like some central system, and then there's a cable wire that goes through the neighborhood, and different homes, when they purchase a cable service, get hooked into that same wire. Okay, so you have many homes in the neighborhood that are connected to the same wire, and inside each home you have some you have the television connected directly to the cable, or maybe to a television cable box. But then you also have a cable modem that's connected to that same shared medium, and all these cable modems are connected to the same medium, and somehow they all give internet access to different users at home. And what's happening here is the use of 3 different multiple access protocols at once. And there's so much care needs to be taken to share this medium because, like I said, it's one big wire that's shared by all these homes. It's a single broadcast medium. When one of these modems, when your computer sends data to, let's say Gmail, you send a message, all of the other cable modems in your neighborhood see that data, although they're not designed to reveal that data. And of course, the data also should be encrypted end to end, which we'll talk about later on. So it doesn't really matter that they see it, but they are kind of all sharing that same channel. They hear each other's traffic, both upstream and downstream. So downstream, there's this CMTS, is the cable modem termination system. You can think of this as something like a kind of router, I guess. But this is a device that manages the connection of all these different cable modems, and it sends down to them internet frames, TV channels, and signaling messages to control the cable modems. And in the reverse direction, the cable modems send their own internet frames, so they send internet data up, and they have to share the channel. So in one direction, we have just one device communicating to many different listeners. So it's a one-to-many broadcast downstream. So downstream, there's no contention. But upstream, you have many different devices that are sharing the same channel to communicate back to this CMTS, which is a kind of router that connects to the rest of the internet. Okay, so they have to all share that medium somehow. And like I said, this happens in several different ways. So there's frequency division multiplexing, FDM, which is a kind of channel partitioning we said last time, that divides this link, this one wire, into multiple channels. And some of them are assigned to be downstream channels, so for one direction, the other upstream channels for the reverse direction. And that allows communication to happen down and up at the same time. It allows multiple down packets and multiple up packets, as long as they're happening on different frequencies. So that provides some sharing. But that's not the only mechanism that's used, because that's not flexible, remember. There could be greater demand from some devices than others, so we don't want to have a channel that's dedicated for every user. So we also have time division multiplexing on those different channels, where we have different time slots. And those slots can be allocated dynamically. We'll see how in a second. There also is a random access protocol during a special time periods when the cable modems request time in the taking turns protocol. And this cable modem termination system is responsible for determining how the time slots are used by the different devices. This will become more clear in the next slide. I'm going to show an example. Now, but one question I want to ask first off is why we don't have to worry about collision on these downstream channels, but only on the upstream channels. Why is that? I kind of mentioned that before. So stop and think about that. The answer is that downstream there's only one device communicating. That is the cable modem termination system. Of course, there could be data coming from all different routers, like a variety of locations on the internet, let's say, end hosts. But those are queued up, just like any other router in this CMTS, and delivered one at a time downstream, broadcast to all of these different devices. Now, in the upstream direction, there are multiple. In this diagram, we see 4 different devices that could start talking at any given time, and that introduces the possibility for collision, right? But in the downstream direction, there's only one device that can talk at any time, so there's no collision there to worry about. So here's a little drawing I made to illustrate this cool media access control that happens with DOCSIS cable, just as an example. So, whoops. In the Y direction, we have different frequencies. So this is showing, remember, this all represents what's happening on a single coaxial cable. So there's only one electrical channel, but it's divided by frequency into, let's say, 5 virtual channels, and those can carry data independently. We assign some of them to be downstream channels and some of them to be upstream channels. Okay, so 3 of them are downstream channels. This is data coming from the internet down to the devices. And we have 2 for data coming from the devices up to the internet. Now, there also could be channels that are dedicated to video service for the televisions, right? But I'm not showing those. And notice that there's more downstream channels than upstream channels. That's typical because, I mean, it depends on how many devices you're using, but typically home internet users are downloading data, not uploading data, and typically they're limited in the speed that they can upload compared to download. So they may only get 1/10 of the upload speed than download, and one of the reasons is that the way that's implemented is by providing more downstream channels than upstream channels. But that's generally what consumers want with home internet service. In these downstream channels, so you also see that over time, the x-axis is time, and there's time division multiplexing in the sense that there are different time slots where data is sent to different receivers. So all this blue data represents data flowing from the internet to different cable modems, and I have 4 different cable modems, A, B, C, and D. So this slot shows data going to modem A. Modem A also gets data in these 3 other time slots. But then there also are times when C and B and D are getting data, right? The CMTS, that kind of edge router thingy that is managing the cable modems in the neighborhood, that device can decide when to send data. So if it has a lot of data to send to A, it can just take up a lot of slots with A, because every device, every modem is listening to these multiple channels, and whenever it sees data that has its address on it, it will pick that up and accept it, but it can just ignore the other packets. So this scheduling doesn't need to be determined ahead of time because it's all being sent by the same central system, the CMTS. In the reverse direction, it's a little more interesting. Okay, in the reverse direction, these 2 upstream channels I'm showing, we have, this is showing 2 different devices, A and B, green and red, that are sending data back up to the internet. And they have certain time periods and channels that they have been assigned where they are allowed to, they have exclusive access to that frequency time combination. And the way that's assigned is in a time slot assignment. There's some of these downstream channels or slots, let's say, some of these downstream segments are dedicated to telling the cable modems when they can talk in the future. So, for example, this time slot assignment here, for example, might have contained the information telling A that it can use this time slot in the upstream channel to communicate data back. Okay, and similarly, this data from B must be happening because at some previous time there was a time slot assignment from the central system telling B that it can send at this particular time. Okay, so this is kind of like the polling system that we talked about, taking turns, right? We have a central controller, which is the cable modem termination system, a central controller that tells all the different participants when they should talk. That assignment that's in the time slot assignment. This is a broadcast to everyone, telling them all when they can talk upstream. Downstream, remember, we don't have to worry about doing assignments. The cable modem termination system will just send the packets it needs to send down whenever it wants, wherever it wants to, and whenever it wants to. Right? It'll have this queued up and it'll send them out whenever. Now, there's more we have to say to complete this picture because in order for the central cable modem termination system to make a good decision about what time slots to assign to different cable modems, it needs to know something about what the demand is for upload from the different cable modems in the neighborhood. Okay, that happens during this time request period. There's a special time period on one of these upstream channels where all the different cable modems that have data ready to send to the internet, they can make a request to the central system, to that CMTS, to ask for time slots in the next period. And now this is open to everyone, and the different devices will make their requests using a random access protocol. So now we're introducing the third kind of media access control system, random access. So in this case, I'm showing 4 different devices, A, B, C, and D, that are all making requests. They each want to upload some data. So these requests will identify themselves and, let's say, the amount of data that they want to send. And they're sent at random times. The requests are sent at random times to reduce the, they don't all send at the first time. If they all sent at the first time period, there'd be a high likelihood of collision. So they kind of randomly give their requests to try to avoid collision. There's no guarantee that they won't collide, though. This is the one part of the system where there's a possibility for collision because everyone has equal access this time to make requests. But so if you collide here, you're unlucky, but otherwise the CMTS will see that C and D made requests for time, and then it should give time to C and D. Now in this case, actually, it gave time to B and A, so maybe this picture is not totally consistent, but maybe this B and A allocation was based on a previous time request that hasn't yet been fulfilled. Right, so again, frequency division multiplexing by having 5 frequency channels and 1 physical channel. Time division multiplexing by having different time slots that are allocated. Taking turns in that this time slot assignment from the central CMCS tells the different cable modems when they can talk on the upstream channels. And during those time periods, there's no collision, right? Because they're explicitly assigned to talk. And then finally, random access happens in these special time request windows on the upstream channels where the different cable modems can request future time slots for uploading data. All right, so overall, it's a pretty sophisticated system that combines many different mechanisms, and it's efficient in the sense that there's very little chance for collision. The only time where collisions can happen is inside this time request area, and it's flexible because if there's only one modem, let's say, that has to send a lot of data, that can happen. That one device can get an allocation of all of the upstream channels if it's the only one that needs them. And same thing with downstream. Cool. Okay, so in link layer protocols have error detection and correction. We also saw this in transport, like with TCP and UDP, and we also saw it in IP. This is especially important in the link layer, especially if we look at like wireless media that are very prone to bit flip errors because of noise. So we're going to spend the most time talking about error detection and correction here. Error detection is just noticing that there's an error. When that happens, the reaction is to drop a packet. Error correction is better. We don't just drop a packet in that case, but we have the ability to fix the packet, the bit error, and deliver the packet. But it's more costly because it has more redundant data. Both of these have redundant data. We add data to the packet in order to allow us to do a detection or to do a correction. Generally, if we're trying to do a correction, we have to add more data to the packet. And we'll just go through that again now in a couple different ways. One simple way to add error detection is with parity. This is when you add an extra bit to some data, and the value of that bit is chosen to make the total number of ones even. Like even or odd, so 2, 4, 6, 8, and so on. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 ones. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9 ones. And I guess in this case, we're using odd parity. So that means that we are choosing the total number of ones to be odd. So we would set a 0 here. If there's an even number of ones, we would have added a 1 to make it odd. Okay, so you can do either even or odd parity. It's the same basic idea. When you have just a single bit like this, you can detect a single bit flip error. If there are 2 bits that flip, then you wouldn't be able to detect that. But there's very little data that we're adding, so that's nice. We can also extend this idea to do a simple kind of error correction with 2-dimensional bit parity. So in this case, we have some data, which is shown in the upper left of this matrix. We kind of arrange it into a rectangular shape, into a matrix. And then in the rows, we compute parity. The parity is shown on the right-hand side. And in the columns, we also compute parity and put that in the bottom. And we also compute parity of the parity. So this is simplest to see by looking at this example in the bottom. So we have some data that's arranged into a matrix. We computed parity in both the up and down directions. So that's all the extra data around the edge. The right and bottom edge is additional parity data. And if a bit was flipped, so let's say that this 1 that's in position, that's in this position changes to a 0, then when we check in both directions, all of the rows and columns, we see that there's an error in one row and one column. So in this case, we were using 1, 2, 3, 4. We were using even parity. So we expect an even number of ones. In this case, there are only 3 ones. That's a problem. Now, just looking at this row, we don't know where the problem is, but we know there's a problem somewhere in that row. But then, because we have column parity as well, we check the columns, we find that there's one column where there's a problem. So this column here only has 1, 1. That's an odd number. We need an even number, so we know there's a problem there. So combining, we know the problem's in this row and this column, so that tells us exactly where it is, right? And then we can flip that bit back to the 1. So because we added a bunch of additional redundant data along this edge, kind of like square root of n amount of redundant data if we have n total data. But that allowed us to do single bit error corrections, which is pretty cool. Now, if you have more than one error, obviously those can conflict and create ambiguity about which bits have been flipped. Like if this bit and this bit down here were both changed, then you wouldn't know which of these 4 bits were the problems. We saw already checksums, which are used in IPv4, UDP, and TCP. And this is similar in principle to parity, but it's more complicated to compute, and it's more robust to multiple bit flips. So it's with parity, you're basically guaranteed if 2 bits flip that you're not going to catch it. Whereas with a checksum, 2 bits could flip and you still might catch a problem. Okay. And I already showed you how this works before. You break up the data into 16-bit integers, you add up the integers, wrap the carry bit around to the bottom, and then invert the result. And that's your checksum. And this is easy to compute with digital hardware. Another variation that's actually used in Ethernet is CRC, which stands for Cyclic Redundancy Check. I'm not going to show exactly how it works, and I forget exactly what it is, but it's an error detection scheme that is also efficiently implemented using basic digital circuits, digital gates, so that exclusive OR circuitry can very easily implement this. And it's common in practice for that reason, because it's fast and simple. And Ethernet header uses a 32-bit CRC. Okay, so moving on to a new topic. A slightly new topic. So Ethernet is probably something you've heard of. It's actually refers to a link layer protocol for wired networks, and these wired networks we're going to call these LANs, local area networks. And you might think, when you think of Ethernet, you might think exclusively of these Cat5 style cables that are twisted pairs with the kind of RJ45 connector at the end and 8 electrical wires. But actually, that's not required for Ethernet. So Ethernet also can work over a fiber medium or Wi-Fi. So maybe not Wi-Fi. Wi-Fi is different. Take that back. Okay, so Wi-Fi has additional link layer and physical layer considerations in addition to the basic Ethernet protocol. Sorry, that's what I was confused about. All right, so with Ethernet, we talk about adapters, which are like the ports or interfaces, like the devices that are connected to the LAN. Every adapter, which is like every plug on the LAN, has a unique MAC address. MAC stands for media access control or medium access control. And this is kind of like a fundamental feature of Ethernet. And these are 6-byte numbers. They're kind of long. They're expressed in hex, so they look something like this. You can see here. And these are permanent. So they're actually assigned at the factory. So if you have a computer with an Ethernet port, or you buy an Ethernet card or something, that port has a hard-coded MAC address that was assigned at the factory. And different manufacturers are given blocks of MAC addresses from the IEEE, who manages MAC addresses, and a single manufacturer will use the same prefix on all their MAC addresses because they comes from a block that was allocated by IEEE. So you can actually kind of tell what kind of device, in some sense, you're communicating with locally by looking at the prefix of the MAC address, although often that refers to like the vendor of the Ethernet chip, which doesn't tell you too much about the whole machine. And MAC addresses are used for communicating within a subnet locally. So we're going to talk more about subnets today and MAC addresses, which I kind of mentioned earlier very briefly, but hopefully it'll make more sense after today. So imagine we have a bunch of devices on a LAN, which could be wired or wireless. They can all kind of talk to each other through this LAN. So this is like a broadcast medium. We'll see why it is later. So when this leftmost machine sends a message, it's heard by these two other machines as well as the router. If this computer is talking to the internet, most often its intention is for that packet to be heard by the router and for the router to forward it on to the rest of the internet. But these neighbors can also see that packet. And the way that packet is delivered specifically to the router and not to these other neighbors is by putting the MAC address of the router on the Ethernet packet that encapsulates that IP packet. Okay, so we're adding another layer to the Ethernet stack, another header, which has MAC addresses. We still have IP addresses on packets. The IP address indicates the final destination of the message. But we know that if we're sending a packet from a local network out to the rest of the internet, that final address is not going to be enough to get it to it will be enough to get it to the final destination, but there are intermediate hops that need to be handled. And for the first hop, to get it to across the first hop, that packet needs an address to indicate the receiver at the other side of that first hop. So the MAC address is the receiver at the other side of a single hop. Okay. So one kind of interesting and tricky question is why we're using a new kind of address, MAC address, instead of just using IP addresses at this level. So to distinguish these different machines on this LAN, why are we using MAC addresses, not IP addresses? Think about that for a second. Although it is tricky, I think the reason is primarily because these devices need to have something permanent when they join the network that they can use to immediately distinguish themselves. So that's why these factory-coded addresses are useful. And also, but having a factory-coded address used for end-to-end addressing across the internet doesn't make sense because this address doesn't say anything about what the specific location is. So the IP addresses are kind of location dependent, and if your machine moves, then your IP address changes. But the MAC address is only used to distinguish between your immediate neighbors, so it can be permanent. Okay. So with Ethernet, we have some headers that are added to your packet. We call this a frame, and we use the term frame because it adds bytes both before and after the payload. So the payload in this case would be an IP packet, an IP datagram. So to be, inside this, we would have an IP address source, IP address destination. Inside that, you might have a TCP segment that has, port numbers. Inside that, you might have an HTTP request or response, But all of that to get a packet across an Ethernet subnet from a certain source to a certain destination, like let's say the router, you need this Ethernet frame to indicate the destination and the source within that one hop, that one link. This frame, this header, includes a preamble. Now, see, we're getting to a pretty low level here, so it gets kind of interesting. The preamble is actually 8 bytes that are always the same, right? So this is not good from an information theoretic perspective. We're kind of wasting bits, but the purpose of it is basically 0101 flipping for 8 bytes. This is used to synchronize the bit clock of the receiver and sender, so the receiver and sender can tell exactly when to expect bits to get their timing synchronized. And then we have the source and destination MAC address. Like I said, after that there's a type, which indicates the type of what's inside. It's just 2 bytes, which indicates whether it's an IP packet or an ARP packet. We'll talk about that in a second, or whatever. And then at the very end, there's a CRC, which is that bit error detection mechanism that we talked about. Okay. The Address Resolution Protocol, or ARP, is used to make a connection between MAC addresses and IP addresses. So really, what it's used is to discover the MAC address for a given IP address. So an ARP request has a particular IP address in mind, or it lists a particular IP address, and the response is the MAC address. So if you're on a LAN, you know your IP address, you want to talk to a certain other IP address on that LAN. For example, you want to send a message to the router, which has a certain IP address that you know. You actually need the MAC address of that machine as well. So we kind of start with an IP address. You need to get a MAC address, and the way you get that MAC address is by making an ARP request. Now, ARP is it's like a directory or discovery system, an address discovery system. What happens is you send an ARP request to a special broadcast MAC address. There's a special MAC address which is all ones, FF, so on, and that address is accepted by everyone on the subnet. So when one of these packets is published with this broadcast address, everyone on the subnet should receive it. They all should listen to it, and they'll look at the request and they'll say, "Oh, is this person?" If it's an ARP request in this broadcast, they'll look at it and see, "Oh, is this person asking about my IP address?" If that request matches my IP address, then I'll give a response listing my MAC address. Okay, so the host assigned to that IP address replies with its own MAC address, and that's how machines discover MAC addresses for IP addresses. So notice that the response doesn't have to be a broadcast, because the response came from a specific MAC address, because when you join the network, your MAC address is hard-coded. Like, this ARP request does have a source MAC address. It just doesn't have a destination MAC address apart from the broadcast address. So the response goes directly back to the requester, and those responses are cached in the hardware of the machine that made the request, and it's called an ARP table in the adapter. Okay, so and there's a TTL like DNS for these mappings, and the typical timeout is about 20 minutes. So this is kind of like DNS. In other words, it's a way of mapping from one kind of address to another, but it's implemented in a different way, and it's just like a local system. So the responses come from all hosts on the subnet, so it's kind of a distributed system. It's not centralized. Ethernet hosts are responsible for advertising their own existence. So if you join a network and you can claim an IP address by just giving responses to ARP requests that list that particular IP address. Now, of course, that also means that you can try to request the same IP address as someone else and try to hijack someone else's IP address on your LAN. That's bad, and that would lead to either a network that malfunctions, or if the switch is configured to address this, it might actually shut off your port if you are trying to use someone else's IP address, and it doesn't like that. Or it might disable both IP addresses in that case. But anyway, because these hosts advertise their own existence, Ethernet is plug and play. There doesn't have to be any central action when a device joins a network, assuming that the devices choose their own IP addresses, which we'll see is not actually usually done, but usually we use DHCP, which is kind of centralized. Okay. Now, to give a little bit more explanation for how MAC addresses are used, let's look at a packet flowing across kind of a mini internet from A to B across one router. So this router is on 2 subnets, and when A wants to talk to B, it needs to have an IP configuration to kind of like work on this little internet. So it needs to know its own IP address, which is 111.111.111.111. It needs to know, of course, the destination address that it wants to send to. The way it got this IP address of the destination might have been from a DNS request. So maybe it had the host name first, and it did DNS request and got that IP address back. this sender also needs to know the IP address of the gateway router. Okay, the gateway router is the router that the router on the subnet to which it can send packets that are destined outside of the subnet. Okay, so in this case, the border route, the gateway router is 111.111.111.110, slightly different number. It got that IP address from its IP configuration. So either this was hard coded or got it from DHCP. A also needs to know its own MAC address, but that's hard coded from the factory, so it knows that. It needs to know the MAC address of the router that's going to send this message to. So A needs to, it knows this IP address of the router, but it needs to also get this MAC address. It gets that from ARP, the Address Resolution Protocol. So the first thing, once A has all that information, it can send its packet. Okay, so it constructs this green packet, which is an IP packet that has a source and destination IP address end-to-end across the internet. But it also wraps this up in an Ethernet frame to get the packet from A to R, just across this first hop. So this Ethernet frame has its own MAC address as the source, and the destination MAC address, interestingly, is the MAC address of the receiver on this first hop, which is this router. Okay, so this E6, E9, that is the MAC address of this particular interface on the router. That has nothing to do with the destination. That's just for this hop. So this Ethernet header here tells the packet that your destination is here. Now that's not the final destination. That's just a intermediate destination. Okay, so these Ethernet headers are not going to be valid across the whole path, but they have to be unwrapped and rebuilt for every hop. Okay, so that packet is delivered. This router gets it. Now notice also that this other machine on the bottom that's kind of falling off the screen here on the edge, it also might have seen this packet, but it ignored it because the MAC address destination didn't match its own MAC address. Okay, but this router did accept it because the destination matched. And it unwraps it, right? So it looks at this IP address, this IP header, and this payload. And this here, because it's a router, it's going to forward this to the destination. So it looks at the IP source and destination, particularly at the destination. It checks with its routing table to figure out where to send it. It decides, it needs to go out on this right-hand link. That's what my routing tables told me, which were determined by BGP or whatever. And so R says this packet needs to go out on the right-hand side. So it needs to construct a new Ethernet packet, Ethernet frame around this packet it received to send it. Okay. To do that, it puts in this new Ethernet frame around this old packet that's being forwarded, it puts its own MAC address as the source. Now notice it's the MAC address on the right-hand side of the router. This router has two MAC addresses, just like it has two IP addresses because it's on two subnets. It also puts a MAC address for the destination. In this case, it knows that the destination IP address is in the subnet on this right-hand side router, so it might use the ARP. It might do an ARP query in this right-hand side subnet to get the MAC address that it needs. Okay, so before it forwards this, it might need to do an ARP request. It gets the destination for B, the destination MAC address for B, which is 49.bd.d2, so on. Puts that in the destination. Wraps up the packet and sends it. And then finally, B will accept it because it sees its own address in the destination MAC address. So the key thing here to notice at this Ethernet layer is that when we send packets across the internet end to end, they change in many ways. So previously, the one thing we said changed, if you really were paying attention, you'll notice that the IP TTL header was the one thing that changed, and then because of that, the IP checksum changed. Basically, remember there was one header in the IP, one field in the IP header that listed the number of hops that this packet should be allowed to survive before it's thrown out. This was included to prevent a packet from going on an infinite loop. So there is a little piece of this green packet that changes. But apart from that, it mostly stays the same. But this outer Ethernet frame in dark blue is totally different for every hop that the packet traverses, because the purpose of that Ethernet frame is just to get the packet across a shared link, across one hop. Okay. We talked before a little bit about DHCP, the Dynamic Host Configuration Protocol. We can talk more clearly about it now that we understand MAC addresses and ARP and so on. So we said before that DHCP was a way for hosts to automatically get their IP configuration. Now, an IP configuration is your IP address, the subnet mask, the gateway address. This is the IP address of the router that you're supposed to send packets that are going to the rest of the internet, and the DNS server address, which you use for hostname queries, right? When a host joins a network, it brings its permanent MAC address, it can send a DHCP request as a broadcast on Ethernet. So it uses this FFFF destination in its DHCP request. This discovery message that's shown in this flow in the bottom is a broadcast. The DHCP server, which is usually the edge router, will see this and respond to it. It's responsible for allocating IP addresses. Of course, all the other machines on the subnet see the DHCP broadcast, the DHCP request that's broadcast, but hopefully you have just one DHCP server that's running to give the response. Otherwise, you'd have conflicts, and it would kind of be a mess. And the actual DHCP protocol is an exchange of UDP packets that are delivered inside of Ethernet frames. So the advantage of DHCP is that it allows machines to plug into a network and automatically get a configuration that works in that network. So in other words, the correct IP address, subnet mask, gateway address, and so on. But the disadvantage of this kind of approach, I'm not sure I would really call it a disadvantage, but I guess the disadvantage of mobility anyway. Or I guess if you don't have mobility, there's a disadvantage. So if a machine is always in the same place, but it's still using DHCP whenever it boots up to get an IP address, then what that means is that it might get a different IP address every time it boots up, which might be unnecessary because it's like physically in the same place. And when that IP address changes, that means that other people in the network can't rely on you having the same IP address over time, can't easily find you, so you can't run a server application as easily if you're using DHCP and your IP address changes. Now again, like I said, if you're mobile, if you're a laptop that's moving all over the world, all over the country, whatever, you want to be able to get different IP addresses so that you can connect to different networks. But if you're in one place, then DHCP kind of seems like it presents a disadvantage in the sense that your IP address changes unnecessarily. Okay. There's a solution to that, which is a static IP address configuration. So a totally static IP configuration actually involves hard coding your IP information. So those four numbers, your IP address, the subnet, the gateway, and the DNS server, and not using DHCP at all. And that's perfectly fine. That's how Ethernet worked in the early days. That's what Ethernet was designed to have hard-coded IP configurations. It's less convenient for users because they have to know those numbers to work. They can't just plug in and operate. But it's simpler and it's more static. So, and this is common for routers and servers to make them permanently reachable by certain IP addresses. There's a way to get the best of both worlds, I guess, of automatic configuration plus static IP address. That is done with what's called static DHCP. So this is where your machine still does make a request to a central DHCP server, but that DHCP server has a database or has a configuration where it actually has a record of your MAC address and the IP address that should be always given back to it. So you've configured this DHCP server to always return a certain IP address in response to DHCP requests from certain MAC addresses. Okay, so you can assign IP addresses to MAC addresses in your DHCP server if your DHCP server allows configuration, which basically all of them do these days. So this gives the administrator one place to track IP address assignments. In other words, that one place is the DHCP server, while also allowing machines to have fixed IP addresses, which can be advantageous. Okay. Now, of course, you might have a machine joined that has an unknown MAC address. In other words, it's not one that we have assigned an IP address to. In that case, what usually would happen is that a dynamic IP address from a pool of unused addresses would be assigned. Okay, so you can have a mixture of machines that are getting dynamic IP addresses and machines that are always getting the same IP addresses. All right, so switching gears just a little bit, but still talking about Ethernet. At this point, if you stop and think, you might be a little confused as to why we're talking about media access control on these wired connections. Because actually, if you look closely at these cables, there are 8 electrical conductors, and on these Cat5 cables. On the fiber optic cables, we have 2 optical fibers. So we have a fiber to send data and a fiber to receive data. So there's no sharing on this fiber, and there's certainly no sharing on this Cat5 cable, actually. So the reason why there are 8 cables instead of 2 is because of the way the signaling is done in pairs and in 2 pairs, just to make it faster and more noise robust. But that's an electrical detail we don't have to worry about. But actually, there are dedicated channels in both directions on both kinds of cables here. So why do we consider it a shared medium? It's actually for historical reasons, and which is, so I'm going to go through a little bit of the history of how Ethernet worked in like the 80s and through the 90s to today to explain why it works the way it does. And we'll see how that in practice, in modern Ethernet, we don't really have sharing, we don't really have collisions, but in the early days there were collisions, and so it's built into the protocol. Okay, but anyway, so let's go back 30, 40 years, 35 years to the early days of Ethernet. And in those days, Ethernet was done on these coaxial cables, the same as what was used on cable television. And you had a bunch of computers with little like BNC coax connectors in the back from their network adapters. And you would connect the machines. If you had 2 machines, you just run a cable between them. If you had more than 2 machines, you would use these like T connectors to like splice into the wire. But basically, you had one wire that connected a bunch of machines. So this was designed. Ethernet was designed to be a really low cost networking tool. I think 3Com was a company that made it really popular and made a lot of money off of it in the early days. And the reason Ethernet took off in the PC era was this was a time when like offices could afford to buy many computers instead of having one big computer, and these are relatively cheap machines, like maybe just costing $2,000 or something. But they still wanted a way to connect them, so they needed a cheap way to interconnect the computers. And this kind of cabling was a simple way to do that. And they didn't want to have some kind of central device or anything else. So it's just this is just a simple way to do it. And we call this a bus topology. Remember, bus is a term we used before when we were talking about the internals of routers. A bus is a shared channel. Okay, single electrical channel. Now later on, this evolved slightly, so that all was fine, but actually it's a little bit unreliable, because if any one cable, if you start to build this out to like dozens or hundreds of machines, then if you have dozens or hundreds of these wires all connected together, if any one of them fails, like has a problem with electrical noise, or a mouse chews on it or something, then that will affect all of the computers. Because like you might split the whole network in half, let's say, which is bad. Okay, so, and also this cabling is kind of expensive with all this electrical shielding and everything. So in the 90s, it became attractive to use a different kind of cabling, which is this twisted pair cabling. And also, we had a lot of IT people that were experienced in installing telephone systems, and this twisted pair cabling is very similar to telephone cables, except there are 8 conductors instead of 4. And yeah, so this was used for instead of coax, but in order to connect multiple machines together in the same way that we had them before, we needed a device that would join all these several different cable ends, I guess, to make one big bus. So the Ethernet hub was invented, which is a device that acts as a bus to share signals from many different computers that are connected with twisted pair Cat45 cabling, let's say, or Cat5 with our RJ45 terminals. Cat5 cabling. And so we end up with not exactly a bus topology physically, but a star topology. So in the middle, you have this hub, and then you have a bunch of devices connected to it. And you have separate cables. So if any one of those cables fails, the other cables can still operate through this hub. Okay. But it has to be designed, these were designed to be compatible with the original coax cable style of Ethernet. Okay. So what these Ethernet hubs would do is mimic a broadcast medium, actually. So in some sense, a broadcast medium is annoying. It's disadvantageous because it creates contention, but it also is a really simple way to join a bunch of machines. So the hardware inside of these hubs is actually really simple. All it does is, so it accepts signals on all these ports, and when a signal comes in, it duplicates it outbound on all the other ports. And if that's all you're doing, then you can, do this on a bit-by-bit basis. So when a bit comes in, when an electrical signal comes in that has high voltage, you just replicate that on all the other ports on this hub. And you can connect multiple hubs together so that if you have a signal going out on this one port, it goes into another hub, and that hub will replicate it out on the other ports. So this diagram shows many computers hooked up to two hubs that are daisy-chained. And when this one machine here has a purple message that says hello, that message is duplicated out on every single other port. So every other machine gets it. And same thing goes for these other machines. That if they want to communicate, they can do that, and it'll be replicated on all the other ports. Okay, so again, a very simple device. It's easy to build. With early 1990s technology, you could build one of these and sell it for like $50 or something, which was, in those days, was cheap for this kind of thing. And that allowed all the machines to communicate using a simple and reliable and cheap kind of cabling, those twisted pair Cat5 cables. Now, the problem, of course, is that there's a possibility for collisions. So if two machines try to send at the same time into two different ports, the hub will try to replicate that, will want to replicate that same message out on all the other ports, but it can't send two messages at the same time. So if the hub detects two incoming signals at the same time, it notices a collision. It lights up a little light here. So if you actually look at this part of the picture, this light says COL for collision. See that? It'll detect a collision, and it will actually send a special jamming signal. So it'll send out data on all the ports that is like bogus data that'll fail a CRC check, and so that packet is dropped. Okay. So so the Ethernet hub implements a kind of shared medium using a bunch of cables that themselves are not shared. The cables are point-to-point, but they're point-to-point between the computer and the hub. So the spokes are point-to-point, but the hub of the spoke, the hub of the star, creates a shared medium, a broadcast medium. So what are the shortcomings of this design, I guess? What do you think? Stop and think about that. If you were to make this faster, how would you do it? What are the opportunities to make this faster? Well, I mean, basically the problem is that these are really prone to collision, right? There's no way, even if you have like 100 ports, only one of the machines can talk at once because its data is replicated out on all the 100 other ports. So notice also when I talk about ports here, I'm talking about physical ports, the plugs, okay, not TCP or UDP ports. So it's not scalable. If we have a busy subnet where a lot of machines want to talk, they're going to have a lot of collisions because only one can talk at once. And another downside, which is a little bit less obvious, is all the machines have to operate at the same line speed because the device works at a bit-by-bit basis. So when these were invented, the two different speed options were 10 or 100 megabits per second, and cheap devices and cheap hubs might operate at 10 megabits, and the other ones might be 100 megabits. They'd have to all be the same speed. Okay, but the first problem is the most important. Okay, this is early to mid-90s. In the late 90s, there were devices invented and adopted to solve this problem, and those are still used today. Those are called Ethernet switches. So notice that our device went from blue to gray, but of course they can be any color. And what Ethernet switches do is avoid collision by avoiding broadcast. Now they don't totally avoid it, but in most cases they avoid collision and they avoid broadcast. And the way they do this is by by storing and forwarding packets and remembering, trying to learn and remember to which specific port the message should be sent. Now, of course, remember these Ethernet networks are supporting generally IP messaging, so every packet generally has a single destination IP address or MAC address, really, a single destination MAC address that it should go. It doesn't need to be broadcast. The only reason to broadcast it was for convenience because we were building a dumb, simple system didn't without a lot of logic, a lot of hardware to handle it. But yeah, so if this message comes in here, this purple one comes in and says hello, there's a specific destination address on that message, destination A. If we know that that machine A is over here on the left-hand side in this first port, then the switch only needs to send it out here. And by making that clever choice and not sending it out on these other three ports, that allows these other three ports to be used simultaneously for other communications. So for example, machine C could say hola on port 3 with different destination E, and if the switch knows that the destination E is on this port 5, now in reality that port 5 refers to a switch that E is on, but same difference. The message supposed to go out here, and then once the message gets here, this switch knows that port 3 is where that message needs to go. Then all this communication can happen exclusively on the ports where it needs to happen, and not be broadcast everywhere, and therefore avoid collisions, allow concurrent communication to happen. We also now, when we do that, we need to introduce storing and forwarding and queuing because we might have contention. Like, for example, if we have two machines, A and B, that want to send a message to C at the same time, it's not shown in the picture, but let's say A and B are feeding packets into ports 1 and 2 with the same destination. The switch can start sending one of them out on this port 3 to destination C, but then what it can do is queue up the other message and send it immediately afterwards. That would be a good thing to do to avoid collisions, to avoid dropping packets, but and make efficient use of the ports. Okay, so they can do that. I mean, the reason why this didn't happen until the late 90s was, well, someone needed to think of it, but also because this hardware is much more complex now. These switches have to have memory. They have to have a forwarding table of some kind. Like, they have to know what ports should be used to send the different devices. They have to parse the packets and look at the MAC address destination instead of just sending out all the bits on every port. So the hardware is a lot more complex. We have parallel packet processing and queuing. So basically, these things are a lot like routers now, except they're working with MAC addresses instead of IP addresses. But by the late 90s, these things could be implemented without too much cost. And like these days, you can get one of these for like $25 or something, pretty cheap. Now, the key trick about this is, how do you know where to send packets? And you wanted to do this in a way that was backward compatible, and it didn't require configuration of any kind. So that without changing the protocols, still assuming that using these protocols that were designed for a single shared coaxial cable that connected a lot of devices, how can you build a switch, a device here that sits in the middle of all these connections, that is able to know where to send packets, on which port to send packets. Stop and think about that. Well, the way that these switches do this is by remembering and learning MAC addresses, or the association between MAC addresses and ports. And so whenever a packet comes in, of course, the switch has to make a decision about where to send that data, but it also knows where that packet came from. If it can look at the source address of the packet and say, oh, that's interesting. I just got on port number 2 a message from address B. Let me write that down, because later on, when I get a message, when someone wants to send a message to address B, now I know that port number 2 is the correct port to send that message on. Okay. Now, initially, the switch doesn't know anything. So at first, the switch does resort to broadcasting. When if this switch is turned off and you turn it on and nothing's plugged in, you plug in a bunch of devices and have them start working, like communicating with each other. For that first packet that comes in, the switch has no idea who's connected to what port. It got its very first packet. So at first, it would have to broadcast that message to all the ports. Okay, but then it will get a response, and now it knows 2 MAC addresses and port associations, right? Because there was a source and there was a destination. So over time, it will gather a complete list of what ports each MAC address is on. Okay. Of course, there's a time to live for those, because you can unplug and replug machines, and you want that to work. But that's the key thing about Ethernet switches, that they remember and learn MAC address port associations. And of course, that also works when you have chaining. So, like, if you connect a second switch to this first switch on this port number 5, then this first switch will remember that port number 5 is the correct port to send packets for E and F. Because when data comes in from E and F, to this switch, it might be broadcast out on all the ports the first time, and then it goes out in particular to this port, and so this first switch learns that port number 5 is the port. The switch is okay with having more than one MAC address associated with every port. It can't have multiple ports associated with a MAC address, but it can have multiple MAC addresses associated with a port. And in particular, that happens when you have a chaining of switches. Okay, so these switches allow a subnet to efficiently grow to be very large, because the packet flows are isolated from each other and can happen in parallel. Another cool thing about this is that there's no special configuration required either on the nodes or in the switches. These switches are totally plug and play. So when you buy a switch, like there's no configuration you have to do. You just plug it into the power and you plug devices into it and it just works. Switches are very easy to use generally, unless you're doing things like VLANs or whatever, which we'll talk about later. Even though these devices can be very sophisticated inside, everything they're doing is automatic. And it's like learned by observation. You can connect more than one switch to each other, and they'll forward each other the appropriate traffic, just like you had kind of the machines plugged in directly to the port. It doesn't matter. And switches, by following those rules, switches eventually avoid collision entirely. Now they don't. They do avoid collision entirely because of the queuing that they do. They eventually avoid broadcast entirely, but they always avoid collision. And internally, you have output queues like routers. You have input queues as well, and you have a switching fabric in the middle. So actually, internally, a switch really looks very similar to a router. Okay. You might, and like a router, those queues could get full, meaning that you have to drop a packet. But that's okay. If you're using either of these kinds of cabling, then a message can arrive on a port at the same time a message goes out. Again, because there are wires for both directions. So we say that this twisted pair and fiber optic cabling are full duplex media, or at least like when fiber optic cables, if you have a pair of them, are full duplex. Each individual strand is not. So you have full duplex is a term we use in networking for a channel, a wire, I guess, or yeah, that has separate signaling channels for sending and receiving. So sending and receiving can happen at the same time. You don't have collision just because you're sending at the same time as you're receiving. Coax and wireless are half duplex media. So half duplex is the term we use when sending blocks receiving. Now, of course, if that's the case, you can use frequency division multiplexing to create multiple virtual channels, so you can send at the same time as you receive. But in general, with a half duplex media, you have to implement some kind of media access control to avoid collision. Okay. So let's look at switches again. And let's say we connected 3 of these switches in this fashion. There's actually a problem here when you create a switching loop like this. Okay, so I want you to stop and think about what problem might arise with this kind of configuration. You have to maybe step through it a little bit. Basically, the problem is that if you have a broadcast where a message is sent out on multiple ports, remember switches do still allow broadcasts if the switch is not aware of that particular MAC address yet, then you'll end up with packets traveling in an infinite loop. So let's say the packet comes in from A, and let's say it's going to B, but it's being broadcast. So it goes out on all the ports. So it goes out on this green port. When it gets to this switch number 2, it goes out on all the ports, including port number 5. When it comes out, gets to this switch number 3, it goes out on the purple port. And then again, it's hitting switch 1, so it goes on all the ports, it goes back out to the green one, and so on. So it keeps going over and over again in this direction, also perhaps in the other direction at the same time. Okay. So that's not what you want. So how about this scenario here? We have a switch with a wire that just plugs into itself. Okay, it plugs port 3 into port 4. Kind of sick. What happens there? Well, the same thing, right? It's with fewer switches, but we still have a loop. So if we have a broadcast on all these ports, it'll go out. The broadcast will go out on port 3 and into port 4. When a message arrives on port 4, it goes out on all the ports, which means it goes out on port 3 and into port 4 over and over again, potentially. So so basically we want to avoid connecting switches in loops. I mean, technically you can actually do this. I did have, at one of the companies I was working at, we wanted to set up 3 data centers connected in this exact same fashion with switches in such a way that there was redundancy, so if any one link was broken, you could still have connectivity. So we did want to have a loop, but the only way to do that and have it work without these broadcast loops is to use what's called the spanning tree protocol, which is a protocol run by the switches to actually decide to ignore one of these links in the loop. But that happens periodically, so that if there's a change, you can recompute it. So if, let's say this originally, let's say that originally this purple link is being ignored. Well, then if later the green link fails, the spanning tree protocol would then later make a new choice of that uses the purple link. Okay. So Ethernet switches are very similar to routers, and for that reason, IP routers are sometimes called layer 3 switches. So layer 3, if you remember, refers to the IP protocol layer. Ethernet is layer 2. So a layer 2 switch is an Ethernet switch. A layer 3 switch is actually a router. Okay. So that term layer 3 switch is a little bit confusing. But with an Ethernet switch, what we have is MAC addresses that are used to determine the outbound link for a packet. Packet comes in, we look at the MAC address, that tells us what outbound link to use. There's an equivalent with layer 3 switches, IP routers, which is that we look at the IP address of the destination and check our forwarding table to determine the outbound link. Okay, so again, there's a different kind of address that's used, different layer, but still we're using addresses to choose the outbound link. In Ethernet, we learn forwarding rules over time automatically by inspecting traffic. So in other words, where's traffic coming in? With IP, we decide forwarding rules more explicitly using BGP and interior gateway protocols. So it's a little bit more systematic. It's not automatic. There's actually a protocol that has to be run to decide the forwarding tables. With Ethernet switches, redundant links are not allowed unless, like I said, you use a spanning tree protocol. With IP at the third layer, at the IP layer, with BGP and so on, we have routing problems that choose the shortest among multiple paths. So it's okay to have multiple redundant links. It's actually desired that you have multiple redundant links, and you can choose the shortest one. With Ethernet switches, there's no configuration at all required. They're plug and play. With IP routers, there's actually a lot of configuration because you need to have the correct IP address assigned. You need to have an interior gateway protocol configured. You need to make sure you're connected to the right neighboring routers and so on. And with Ethernet, one of the downsides is that broadcast traffic, whether ARP or DHCP, has to be sent out on all the switch ports and through neighboring switches. So if you have thousands of nodes, once you start to reach thousands of nodes in an Ethernet LAN and a subnet connected through switches, this broadcast traffic starts to become a really big load on the network, right? Because anytime anyone does anything with DHCP or ARP, everyone has to hear about it. With routers, you're isolating Ethernet broadcasts to different subnets, so IP routers themselves don't transmit broadcasts. And another benefit of routers is that they give administrators greater control over where traffic is sent, so you can implement those local preference rules in BGP to do what's called traffic engineering. Whereas with Ethernet switches, you just kind of you don't have redundant links, and so there's not that level of control. Okay. So the purpose of this comparison is to understand why there are two different levels of essentially switching, or two different ways to decide how packets are sent throughout a network. But this Ethernet switch-based routing is very simple. It's not routing technically, but it's something like routing, and the IP routing is much more sophisticated. So we can look at a simple campus LAN to see where switches would be used. So we might have one router at the edge that connects to the rest of the network, or the internet in particular. And there might be one central switch that is fast and connects maybe some servers in a data center that everyone connects to and the outside world connects to, as well as connecting to other switches that are in different parts of the campus, different buildings, and inside each of those buildings you might have a lot of computers that are connected to those building switches, right? So 2 levels of switches in this case, or even 3 levels if you consider this other one here, and but only one router that connects all of them. So all these machines in the subnet can communicate directly with each other, sort of in quotes, at the IP level. So this machine can talk to this mail server without going through the router, but it is going to go through several switches, but it won't necessarily know that those switches are there. It doesn't have to know those switches are there. This machine can put the MAC address destination of the mail server on its packet and send it, and it will get there without that Ethernet packet being changed at all. One little side note on switches. Big switches, not home switches, but kind of enterprise switches, support virtual LANs or VLANs. This is a way to take a single physical switch and configure the ports on them to belong to different virtual switches, essentially. So you can say, I have a switch with 16 ports, but I want the leftmost 8 ports to all be permitted to talk to each other, but the rightmost ports cannot talk to each other, or like they can talk to each other, but not across the middle, right? So we have a blue virtual switch and a yellow virtual switch. So we have one department on one of them and another department on the other. They can't communicate directly. If they're connected in this way, then only the blue ones will be able to talk to each other and the yellow ones would be able to talk to each other. Kind of like having two different physical switches. And if you wanted to interconnect them, you could of course put a wire across the two VLANs. This is done to create like private subnets to isolate traffic for security reasons. If you have certain machines that are not supposed to talk to others, without having to like buy a lot of different little switches. Sometimes it's easier to just buy one big switch and then configure it into like little pieces using VLANs, virtual LANs. Although these different subnets could talk to each other through a router. If they were all connected to a router, if they were all connected to the internet, for example, they could all talk through that. Right? So speaking of switches and big networks, data centers, of course, have like thousands and thousands of machines in racks. So I kind of see in this picture, racks of servers that might be in a data center. And you have applications that are running across all of these machines, perhaps that talk to each other. You might have a database in one of these racks and a web server in the other. They need to talk to each other. But in order to support communication at this scale, you need kind of a hierarchy or a tree structure of switches. So you might have top of rack switches at the lowest level that connect all the machines in a single rack. And then those top of rack switches connect to perhaps a tier 2 of switches. And those switches connect to a higher tier, which connect maybe to routers. And finally to a border router that connects to the rest of the internet. So that design is simple, but it creates perhaps bottlenecks at some of these upper switches, because any communication between anyone in the left-hand side and the right-hand side has to flow through these two switches, right? One way to reduce that bottleneck is to have sort of a complete bipartite graph connection between these two levels. So have a lot of these tier 1 switches and have each of them connect to all the tier 2 switches. And that means that you can spread the across data center network across more switches. That does introduce some loops in the routing, but if you implement a spanning tree protocol, you can avoid misusing those loops in broadcasts. Okay. But we're not going to talk a whole lot about this stuff. We're just kind of giving you a taste of it. I also want to give you a little taste of what happens in supercomputers. So this is another kind of computing environment where networking is incredibly important. And so this picture shows the Titan supercomputer at Oak Ridge National Lab, which if you look closely, I guess I'll zoom in, each of these little cabinets has a rack of like maybe 20 or 40 machines, and overall there are thousands of computers here. They're all connected in this one huge room. And so it kind of looks like a data center at a high level, right? You have all these racks of computers that are all connected to each other. But the big difference about these supercomputing, or sometimes it's called HPC, that stands for high performance computing. The big difference here is that the whole purpose of building all of these computers is to be able to run a single computation, a single distributed computation at once across all of these. If you wanted to just support a lot of like little programs happening at the same time, you might as well just have a bunch of little computers that are on people's desks all around the world, right? The purpose of a big supercomputer is to do calculations that are not possible on smaller machines. Okay, and because you're doing a distributed computation, that's very different than data center, by the way. Data center is designed to run a business that has a lot of like parallel transactions, so there's a lot of like little stuff happening in parallel. But not coordinated, not related stuff, all independent stuff happening in parallel. In this supercomputer, we have parallel stuff that is all like, it has to be coordinated constantly, right? So there's a lot of communication between these devices. This is perhaps one of the most challenging network environments you might face, where there's the highest degree of performance required. So interconnect is the word that they use in supercomputing for the networking. So the interconnect speed often is actually more important, or the most important design criteria of a supercomputer, because you have like tens of thousands, hundreds of thousands of nodes that need to be involved in this calculation, and if they can't communicate efficiently, it's going to be really slow. So one important difference here, because of the need for low latency communication and the lack of need for some of the other things that are required in data center and like commercial networking and the internet, a different kind of link layer protocol is used here called InfiniBand. So InfiniBand is an alternative to Ethernet that's used most often in supercomputing, and this is what this. So InfiniBand is a combination of a physical communication channel and a different set of link layer protocols instead of Ethernet that allow low latency communication between machines, and actually because it doesn't have things like IP addresses and TCP ports or UDP ports, you can have a packet that is addressed to go to one of the neighboring machines or a machine across the supercomputer, and when it arrives, instead of having to be checked for the IP address and or MAC address and port and handled by the OS with an interrupt handler and delivered to the appropriate process, instead of all that happening, which introduces latency, the receiving machine can actually immediately write the received data to memory and allow that program that needs that data to start using it immediately. So you can this allows really a much lower latency, and it doesn't have the same kind of like security, like the same isolation of networking and processes. So it's like less secure in some sense. But this is an environment where security is not the goal. I mean, you're running a system with one program running on all these machines basically. So there's no need to protect it from anything, because the only other things running are other copies of the same program. And if you want to learn more about supercomputing, check out Computer Engineering 358, Parallel Computing, which discusses the different network topologies that are used here. Okay, so that concludes our discussion of Ethernet, and we're kind of done moving down the networking stack to the lowest level we're going to go. We're going to come back to talk a little bit about security and mobility in the middle of the stack, but we've kind of moved from application layer all the way down to the physical link layer. And now we should be able to have a pretty clear idea of what happens when you make a web request at like much more detail than we knew before. So let's consider visiting the google.com website in this scenario here. So we have our laptop connected to a school network. Open up a browser. Okay, we want to fetch the web page that's stored in a web server. Okay, so the first thing that happens is that we connect to the network. We need to, what we do is first we make a physical connection, like let's say we plug in or we connect to the radio channel with Wi-Fi. DHCP is used to request your basic IP configuration, your IP address, first hop router, DNS server address, subnet mask. That DHCP request is encapsulated in UDP. Inside of UDP, the UDP packet's is put inside of an IP packet, and that's put inside of an Ethernet frame. The IP address actually is not really meaningful in the DHCP request, but the Ethernet frame has the broadcast destination address as the destination, so everyone on the LAN hears it, including the DHCP server. DHCP server gets the that packet, it unpacks it, and gets that UDP message that is a DHCP request. The DHCP server creates a response, and it addresses it back to the client, and wraps it up in those same layers and sends it back. And now the client has its IP configuration. Now, it wants to make a request to google.com. In order to do that, it needs to make a DNS request to get the IP address for google.com. So it constructs a DNS request, which is in a UDP packet, UDP segment. Again, that's inside of an IP datagram, which is addressed to the DNS server. It just got the DNS server recently from DHCP. Now that needs to go inside of an Ethernet frame to go to the DNS server, but we don't have we're not going to use the MAC address destination of the DNS server. The DNS server is outside the subnet, so we need the MAC address of the router to put on this DNS request, because we want the router to take that packet and forward it to the DNS server. To get the MAC address of the router, the client needs to do an ARP request, an ARP query. It knows the router's IP address, that is in the ARP query, but it broadcasts that ARP query to everyone on the subnet, and the router is the one that responds because it sees that its IP address matches that in the ARP query. It sends back its MAC address. Now the client has the MAC address of the router, and it can send its DNS server request. Okay. Now that DNS request, now that it has the MAC address of the router, gets sent to the router. The router gets it. It actually unpacks that Ethernet frame. That Ethernet frame is no longer useful because that was just for the one hop. The router examines that packet. It sees the IP address destination, and it looks at its forwarding tables to determine which of the links it has to forward that packet to reach the DNS server. The DNS server is way out here in the ISP's network. Those forwarding tables were predetermined by BGP and the interior gateway protocols, which we're not showing here. That already happened before. So the router chooses the correct outbound link and constructs a new Ethernet frame around that packet to forward it to the final destination. And that process repeats at every single router until it finally reaches the DNS server. DNS server gets it, and it gives a response. Okay. The client has sent a DNS server, it got a DNS response, and now can finally make the connection. But to do that, it needs to set up a TCP connection. Okay. To send an HTTP request to fetch the web page, it needs to set up a TCP connection. That involves a TCP handshake. So again, like all these things involve, MAC and IP and everything. We're not going to show that for every step now. I'm just going to assume the packets get to the destination. At every hop along the way, a new Ethernet frame is constructed, yada, 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 yada. The SYN packet, though, goes to the server. The server accepts it and sends back a SYNAC, which gives the correct sequence numbers and flow control window size and all that stuff back to the client. The client's gotten the SYNAC. Now it can start sending the data of the HTTP request inside of that TCP socket. Now that HTTP request has headers that are human readable, and that is sent through TCP to the web server. The web server gets the request, and it generates the appropriate HTML and sends it back. Okay. All right. Yay. That's the magic of the internet. Finally, the web page is displayed. But, there are a lot of steps that happen across many different layers to solve the various problems of the internet, including today we were just talking about handling a single link to get packets across a single hop in the network or within the subnet if you're talking to your neighbors. But then all those other protocols deal with routing across multiple hops, reordering packets, dealing with lost packets and all that stuff, and implementing an application. Okay, but to recap today, we talked about different mechanisms and link layer protocols for doing error detection and correction, very briefly, Parity, Checksums, and Cyclic redundancy checks, CRCs. And then we talked about Ethernet. And the biggest concept there was MAC addresses that were introduced to identify sources and destinations on a shared link. And those are factory determined, they're hard-coded. ARP is a protocol, address resolution protocol, that uses Ethernet broadcasts to find the MAC address associated with an IP address. DHCP also uses Ethernet broadcasts to give clients their IP configuration, IP addresses, and so on. And we talked a little bit about how about switches and how they evolved. So in the old days, Ethernet hubs broadcasted all the data that was received on any port to all the other ports. Those evolved into switches that learned and remembered which specific ports are connected to what MAC addresses, so that received data could be stored and forwarded to just the correct output port, which is kind of similar to what a router does, but simpler. So we call this a layer 2 switch, and we call routers sometimes layer 3 switches. And then briefly, VLANs are ways to create multiple isolated LANs on a single switch if you have a big switch that you want to break into little pieces. And then we looked briefly at data centers and supercomputers as locations where the latest and greatest ideas in link layer protocols and all aspects of networking are relevant and important. So looking forward, we're going to talk about, it looks like we come to the end of the class, but we haven't, because we have important lectures on security and mobility and so on that we're going to cover to give us a little bit more detail and talk a little bit about some modern issues that have come up and modern advances in application layer protocols as well. All right, thanks for joining. See you later.